Taylor series are a special type of power series. The term Taylor series is used when a power series is built from a function. Now let's assume that f of x does in fact have a power series representation about c. And this is just a power series. Remember, in the previous video we discussed what a power series is. So f of x has derivatives of every order. Like we looked in the previous video, you can find derivatives of any power series, so long as the conditions of the interval of convergence are met. Now, we need to determine the coefficients a0, a1, a2, a3, and so on and so forth. Now, to get a1, just choose x is equals to c and plug it into the power series representation. So all the terms with x minus c, remember, if you plug in x is equals to c, so all these terms become 0. So all these terms here become 0. All of them are gone. So what you remain with is a0 is equals to fc. So that's one of the coefficients that you're looking for. So a0 is equals to fc. And then we can carry on to find the derivative of f of x. So you can find the derivative of f of x, which means we are going to differentiate it term by term. Now, if you find the derivative of f of x, then what you'll end up with is this derivative function. So basically, what happens is a0 is a constant. If you differentiate it, it becomes 0, so it's all gone. And then the next term, which is this one here, the second term just becomes a1. So, and that's just how you differentiate polynomials. The powers of x reduced by 1, and you multiply that by, using the power rule. So basically what you end up with is this derivative here. Now, if you plug it, x is equals to c, into this derivative function, what happens is that will be 0, that will be 0, that will be 0, that will be 0. So what you remain with is f dash c. So the value of this function at x is equals to c will be equal to a1. So the value of this derivative function is just at x is equals to c is a1. Now, to get a2, we can find the second derivative of the original function, or just find the derivative of the first derivative. So what you end up with is this second derivative function. Now, and if you plug in x is equals to c, all the terms, so if you plug in x is equal to c, so all these terms become 0. So basically that will be 0, that will be 0, that will be 0. Sorry, not that really. This one becomes 0. So what you remain with is the value of the second derivative at x is equals to c will be equal to that. Okay? And you can continue this process. All right? You can continue this process to find these coefficients. So to get f3, you find the derivative again. You plug in x is equals to c. So all the terms x minus c become 0. So you end up with f3 being equal to that. To get the f4, again, you find the fourth derivative, you plug in x equals to c, and then you end up with f4 being equal to that. Now, I'm not sure if you can see a pattern at this stage of these coefficients. So if you put all these results together, then you end up with this. Now, these are the coefficients that you end up with. If you look through, you can see that looks like in general, we've got a formula for the coefficients. So the nth coefficient will be equal to the nth derivative. Remember here we have zeroth derivative. Um, just remember that f 0x is same as f of x. All right. So the nth derivative at c, the nth coefficient will be equal to the nth derivative at c divided by n factorial. Remember again, 0 factorial is equals to 1. Okay, so that's the pattern, and from that pattern we can make this conclusion that the nth coefficient is given by this formula. All right, and you can see from these results why we are generalizing that the nth coefficient is given by that. All right, so remember we started with a power series representation of a function. So originally what we had is this formula. All right, this one here. So how about we focus on this guy here? All right, we've already generalized that the nth derivative, nth coefficient is equals to the nth derivative at c divided by n factorial. So what we can do is we can plug, instead of writing s sub n, we'll just write what we have, the expression for the nth coefficient. So instead of that bit, we can write this. Okay, let's just get the whole thing this one. So that's in place of s sub n, we can write the expression for the nth coefficient. And hence, we can generate a Taylor series. This is basically what a Taylor series. All right, we can generate a Taylor series. So this, what you end up with is what we call a Taylor series. All right, what you end up with here is what's called a Taylor series. So this is, and you can generate a Taylor series for a certain number of terms that you've been asked, and we'll look at that when we'll be solving questions later on. Now, remember, this is centered at C, but now if it's centered at C is equals to 0, right? If you plug in 0, then what you end up with is a Maclaurin series, okay? If you plug in 0 in place of in place of C, then you end up with a Maclaurin. So basically, every Maclaurin series is a Taylor series, but every Taylor series is not a Maclaurin series. Okay, I'm now going to look at an example. Now remember, a Taylor series is actually, the formula for Taylor series is given in your formula booklet. Okay, so whatever you want to use it, here it is. All right. You don't have to cram it. All that you have to do, and both of them, Maclaurin series and Taylor series, they're in your formula booklet. So wherever you're trying to work out something, just refer back to that. All right. And this is the Maclaurin series. All right. So find the Maclaurin series for this function. So what you're going to do is to start by finding the derivatives, but of course you know the formula from the formula booklet. So from formula booklet, and so on and so forth. We have all this from the formula booklet. So what you're going to do is to find these coefficients at c is equals to 0, and then we should be able to end up with a Maclaurin series for this function. So let's start by finding the derivatives. So f of x will just be equal to e to the power x. F dash x will be equal to e to the power x. And it's the same thing all through, you know. The third derivative is the same thing, and we don't have to keep on going ahead. So basically what I'm going to do is to find the value of these derivatives at uh, at t is equals to 0. So that will just be equal to 1. That will be equal to 1 as well. Okay, and now what you're going to do is to plug these results into the formula. So what we'll end up with is now remember, this pattern here goes up to infinity. So what we'll end up with is f of x will be equal to 1 plus, because f of 0 is 1. Now f dash 0 is 1 as well, so that will just be x. Second derivative of 0 is equals to 1, so we'll just end up with x squared over 2. And then third derivative, if you want to continue, it will just be x to the power 3 over 3 factorial. And this gone on, so the nth derivative will be, if you look at the pattern here, it will just be x to the power n over n factorial, and so on and so forth to infinity. All right. So basically what we can say is we can go ahead and just write this as a power series. So f of x will be equal to the sum from n is equals to 0 to infinity of the nth term, which is x to the power n over n factorial.